All right, so just like calcium calmodulin kinase, AMP kinase can come in and code for the high intensity exercise to phosphorylate HDAC, cause it to release MEF2, and then have 14-3 bind it and take it out of the nucleus. But it doesn't phosphorylate Krebs or one of the ATFs to occupy the CRE site. So how does high intensity exercise occupy or increase the CRE activity? So this is the Egan study that we've looked at, where you're looking at low intensity and high intensity exercise, 0 through 19 hours after the exercise or right before the exercise. And what you can see is that at low intensity exercise, there's no real activation of AMP kinase. High intensity, we activate AMP kinase. Low intensity, there's a nice activation of ACC, even though you can't see phosphorylation here, because the non-phosphorylated still has 3 times more activity if it's, threefold more activity if it's AMP bound or bound to one of these. So you can change its activity without definitively changing its phosphorylation. But this is a much higher effect here in the high intensity exercise. Now, the difference here in high and low intensity exercise might be more related to this low intensity not really changing P38 activity, whereas high intensity exercise is having this nice increase in P38 activity that's there for at least at the 0 hours and maybe at the 3 hours as well. This increase in P38 activity is causing the phosphorylation of ATF2. And you can see that there's more ATF2 phosphorylation both at the 0 hour and maybe a little bit more at the 3 hour. And so what this is suggesting is that maybe AMP kinase is doing the phosphorylation of HDACs, and P38 could be one thing that could be occupying the CRE by phosphorylating ATF2. And so P38 is an interesting one because they're P38 knockout animals. And again, this is looking at PGC4 alpha mRNA. And this is, again, from Zhen Yan's lab, who did the Akimoto study. And what they did here is they either put in, they had the PGC4 alpha knockout animals, and then they put back the alpha form, the beta form, or the gamma form of P38. And they looked to see whether if they stimulated or exercised the muscle, do you need one of these P38s in order to stimulate or show PGC4 alpha mRNA transcription? What they show is that when you put back P38 alpha, when you knock out the P38 alpha, you get good activation of PGC4 alpha transcription. When you knock out the beta, you get good transcription. When you knock out the gamma, now what you see is you don't get transcription of PGC1 alpha. So basically what they did here, I'm sorry I got it wrong, these were short hairpins, so these are knockdown experiments, where you put in the vector, you put in the knockdown for alpha P38, the knockdown for beta P38, or the knockdown for gamma P38. And when you knock down gamma P38, you block PGC1 alpha induction by endurance exercise. So what this is saying is that metabolic stress is activating AMP kinase, that's phosphorylating the HDACs, releasing MEF2, and the stress of the exercise is activating P38, and P38, specifically the gamma isoform of P38, is causing the phosphorylation of ATF2, and that ATF2 can take the place of the Krebs at binding to the CRE. Now you've got the MEF2 from AMP kinase and the ATF2 from the stress and from P38 MAP kinase, and now you've got the MEF2 and the CRE present, and so now you get an increase in PGC1 alpha transcription.